All right, guys. So we just want to finish up the energetics that we was looking at from yesterday. So I'm looking in particular at the heat of neutralization. So just to recap, we said that the heat of neutralization is the energy change. And remember, when we're talking energy change here, we're talking enthalpy change, right? And the energy we're talking about is heat. So the energy change which occurs when 1 mole of water is formed during a neutralization reaction between an acid and an alkali, right? So the heat of neutralization for any strong acid and any strong alkali is about negative 57 kilojoules per mole, right? So since this energy change is a common reaction, they have been able to kind of ascribe this value here, and basically when we look at this working that we're gonna do in the example, you'd realize that's pretty much close to this. Now you need to remember this formula here. Where's my pen? We need to remember this formula here, right? This guy here. Yes, horrible. So I'll just use this tool instead. Right, so you need to remember this formula here, right? Mainly because when you look at the example, you're gonna have the final mass of the solution which you need to calculate, and then you're gonna get a temperature rise. Usually it's either given or that's what we need to calculate. And then the specific
temperature rise?
Yeah, the temperature rise. Because when you add the acid to the base, what's gonna happen is the temperature is gonna increase. Right, because there's an exothermic reaction, so it's going to give off heat. So that means you're going to see a temperature rise. And then a specific heat capacity of water, where we know that's a constant, is a standard, and it's given right here. Right, this is our specific heat capacity of water right here. So that's what we're going to be using, right? So let's clear all those drawings and let's look at the example now. So in the example, they're saying that 50 centimeters cube of a 1 molar sodium hydroxide solution at room temperature was placed in a plastic cup, right? Most of the time, we'd use a Styrotex cup for this because it's an insulator. Able to track the heat change. 25 cm cube of a 2 molar hydrochloric acid at the same temperature was added to the alkali. So this is a neutralization reaction. The temperature of the mixture rose by 9.1 degrees Celsius. Calculate the heat of neutralization. So before we get into like doing any heat of neutralization calculation, the first thing we need to know is how many moles of sodium hydroxide is reacting with how many moles of hydrochloric acid. Right? So this is similar to
how are you supposed to know where you're supposed to do things?
Right. So most of the times, and this is similar to for your titration questions, you need to take out what you have, right, or what you're given. So you see here they say 50 cm cube of 1 molar per dm cube sodium hydroxide. It means therefore that the concentration I want to do this. Right. So the concentration given is is 1.0 moles per dm cube, right?
Okay.
Agreed? So that means 1 dm cube is equivalent to 1,000 centimeters cube.
Yeah.
Agreed? Right.
Yeah.
So in essence, what they're saying here, this is for the sodium hydroxide. This is for the NaOH, right? What they're saying is that in every 1,000 centimeters cube, right?
Yeah.
There is 1 mole of sodium hydroxide.
Okay.
So therefore, in 1 centimeter cube, there'll be 1 over 1,000. moles of NaOH. Somebody messaging group?
I think so.
Yeah, I think so too. Just now how to come out of this first, right?
Okay.
So once we know how many moles is in 1 centimeter cube, we need to find how much is in 50 centimeters cube, because that's how much we actually working with, right?
Okay.
So because
So
on the board, you can just check this on your calculator quickly. So that's 1 divided by 1000, right? Which should be 0.001 multiplied by
50.
Yes.
That's 0.05.
Right. So 0.05 moles of sodium hydroxide is being used at the moment. Right. Let's just make this a smaller.
So you're trying to, so when you figure out what you have to find, you're trying to bring what you already have to the same unit.
Yes. Like exactly. That's what we're trying to do. So before you get to finding anything, you're doing exactly that. You're trying to work out how many moles of sodium hydroxide is reacting with how many moles of hydrochloric acid. So we're going to do the same thing now for hydrochloric acid.
Yeah, I'm here.
Oh, you're there. Okay, you get through. All right, I think you have to lower your speaker. Something.
Okay.
Something giving some feedback. Either it's your speaker. I think it's the speaker. Your volume too low. You have a headset by chance? Yeah, that's much better. You hear me though, right?
Yeah.
All right, excellent. Good. Right. So where were we? Right tree. Right. So we're looking at this example here, right? And what I was saying is that to get started, we're looking at this first bit here. It says 50 cm cube of 1 molar sodium hydroxide solution at room temperature was placed in a plastic cup, and 25 centimeter cube of 2 molar hydrochloric acid at the same temperature was added to the alkali. The temperature of the mixture rose by 9.1 degrees Celsius. Calculate the heat of neutralization. So before we get to the part of calculating the heat of neutralization, we need to extrapolate the information that we need in order to work it out. So first thing we're doing is we're actually working out how many moles of hydrochloric acid and how many moles of sodium hydroxide is reacting with each other. And I did my little calculation to the side here, and it's basically the same thing that they're doing on this side. So you want to find out how many moles is in this 50 centimeters cube of sodium hydroxide, and how many moles of hydrochloric acid is in this 25 centimeters cube. To do this, you use the concentration, right? So we use the concentration of 1 mole per dm cube just now. Knowing 1 dm cube is equal to 1,000 centimeters cube, we now say that the 1,000 centimeters cube contains 1 mole of sodium hydroxide. So if I know what 1,000 contains, I find for 1 cm cube, and then I find for 50 cm cube, right? So we do this similar calculation for the hydrochloric acid. Let's see how good my writing is.
Sir?
Yeah?
What's the difference between like the concentration and what we found before, the 0.05 moles?
Right, so the concentration is going to be, the concentration is the amount of the substance in 1,000 or 1 dm cube of solution.
Okay.
So it's a standard. So when you're talking concentration, you're talking basically like the molarity of the solution. And that's always out of 1,000 centimeters cube. So if I say there's 0.1 moles per dm cube, that means in every 1,000 centimeters cube, there's 1 mole of sodium hydroxide. But the concentration is going to change if I reduce the volume. So that's why I have to work out what is the concentration or what is the amount of sodium hydroxide in 50 centimeters cube of the solution. Oh, no?
No.
No? All right. So, for example, here we say in the hydrochloric acid, right, is a solution that is a 2 moles per dm cube. What that means is that in every dm cube, there is, or every 1,000 centimeters cube of HCl, there are 2 moles. So how many moles are there in 25 centimeters cube? Pretty much, that's what we say. You understand?
Yeah.
That's basically what we're doing. So to find that out, if we know 1,000 cm cube contains 2 moles of HCl, what's that? Then 1 centimeter cube contains 2 divided by the 1,000 moles. Correct, right?
Yeah.
Yeah? Or let's go back to the apples. Therefore, 25 centimeters cube contains 2 over 1,000 multiplied by this, 25. You see that there?
Yeah.
And you're going to get 0.05 moles of HCl. At this point, right, now that you've finished calculating the concentration of each, right, so we have the concentration of, for the 50 centimeter cube of sodium hydroxide, and we have the concentration for the 25 cm cube of HCl. We need to look at the equation. This is where the stoichiometry comes in now. Stoichiometry means that when you look at a balanced equation, right, it's a ratio. There's a ratio of 1 sodium hydroxide reacting with 1 hydrochloric acid to produce 1 sodium chloride and 1 water molecule, right? So we can check it in terms of moles. So 1 mole of sodium hydroxide reacts with 1 mole of HCl to produce 1 mole of sodium chloride salt and 1 mole of water. So it's a 1 to 1 to 1 to 1 ratio, right? So if I have, I know for a fact that I have 0.5 moles of sodium hydroxide reacting with 0.5 moles of HCl. That meets my 1 to 1 ratio here. So that means, therefore, it's going to produce 0.05 moles of water. Let's see if they have that.
So I have a question.
How
you just write the equations for these things?
Well, you had to know your basics. You had to know that acid reacts with a base to form a salt and water.
Okay.
So that's back to acids and bases topic. Right? And then you had to incorporate balance in the equation as well. So you need, well, there's a lot of things going on there. So first you need to know the ionic compounds. So sodium hydroxide is an ionic compound because it's made up of a metal and a non-metal. Right? So you need to know your charges there. Sodium has a charge of +1. The hydroxide ion has a charge of negative. So that's why you're coming up with the formula NaOH to say. Right? Same thing happens to this. H is a 1 plus, Cl is a 1 minus, so that's why I come up with the HCl formula. Then the combining of both of these is an alkali with an acid. And alkalis with acids usually produce a salt, right, and water. So the salt comes from the cation of the base and the anion of the acid. Leaving this and this free to form a water molecule. See that?
Yeah.
So you end up with a salt and water. And that's what you get. Anytime you react any base, so even if I had like calcium hydroxide, now with calcium hydroxide might be a bit different because calcium is in group 2. So this is gonna be like this. Plus, let's say sulfuric acid. Sulfuric acid is H2SO4 because the sulfate is a 2 minus.
But how do you know if you have to put the OH in brackets or not?
Right. So remember, calcium has a charge of +2. OH
Negative.
has a negative. So in order for me, right, to remember the calcium has 2 electrons on the outer shell, so it needs to loan 1 electron here.
Okay.
You see that?
I wasn't even thinking about that.
And another electron there in order for them to balance off.
Okay.
You need 2 OH ions in order to give your overall charge as 0 here. Same thing happening here. This one is a plus, and this one is a 2 minus. So you actually need 2 of the H's now in order to accept the -2 here. Because this has 2 electrons to share, or to give away more or less, to lose. Right? So you need 2 of these 2 H's in order to balance off. Right? So that's a bonding. But then what happens on this side is that you're going to form a salt and water. So we know for a fact that you're going to get water on this side. Right? Because it's an alkali and an acid, or base and acid. And here we know we're going to get salt. And the salt here is going to be calcium sulfate. And we wouldn't have to put anything in brackets here because calcium is 2 plus, sulfate is 2 minus. So that'll just work out like that. What we may need is a number in front of this. Because now we have what? 4 H's in all and 2 O's. So we could probably put a 2 here, and that should balance my equation. Now the point that I'm going to make, this is actually very applicable. Stoichiometry now tells me that 1 mole of this, let me just change my color. 1 mole of the calcium reacts with calcium hydroxide, reacts with 1 mole of this to produce 1 mole of the salt, but 2 moles of water. Right? And I'll tell you why that is important. Let's see if I could just leave these unscrewed up a bit. Right. This is why this is important now. Now check this out, right? They say in here 1 mole of sodium hydroxide reacts with 1 mole of HCl, forming 1 mole of water. We saw that from the equation before, right?
Yeah.
Remember that? It was a 1 to 1. So that was the equation there. Right? So 1 to 1 to 1 to 1. Now they're saying, since we know that that's the ratio, if we're working with 0.5 moles of sodium hydroxide now, and 0.05 moles of sodium hydroxide reacting with 0.05 moles of HCl, we're still maintaining that 1 to 1 ratio. So therefore, we're still going to get 0.05 moles of water. That's where the stoichiometry comes in. Right? So similarly, using this other example after the top here, if I have 1 mole of calcium hydroxide reacting with 1 mole of sulfuric acid, I know I'm going to liberate 2 moles of water. So if I go to 0.05 moles of this reacting with 0.05 moles of this, I'm going to get 0.1 mole of water.
Okay.
You understand how it works? So you use these figures in front of here in order to find out what the ratio is. So if 2 of these on the side combine to produce 1 of each of these on the left hand side produces 1 on the right hand side, or if 1 of each of these on the left hand side produces 2 of these on the right hand side, like more calcium hydroxide example. Follow me there so far?
Yeah.
So all of that was just reasoning it out. We didn't start to do any working yet. We now go and get to the working. So now we're at this point and we know that 0.05 moles reacted with this, and we know how much water was formed, right? We are at this point here now. Where is my highlighter tool? Right, so we're here now. So we know that this is what happened. Now, we want to go back to
straight
that.
line.
Yeah, I know.
Your lines, it's okay. It's okay.
There's a straight line too. Aha. I've mastered the straight lines. Alright. So now that we know how much water was formed, right? So all of that was to figure out how much water was formed. Because what we want to do really is we want to use that formula they have to the top. Because initially when they start the topic, they make it look real simple and say, well, yeah, if you just want to find heat and neutralization, you just need to use this fancy formula here and you're going to find it out. But nobody told us that we had to like work out those individual stuff to find out what the mass of the solution was and what the temperature rise and that kind of thing was. So going back to here now that we know 0.05 moles of water is formed, we're now going to calculate what the final volume of the solution was. And now one is not too difficult because we started with 50 cm cube of the sodium hydroxide, and then we added 25 cm cube of the HCl. So, I mean, it's not rocket science. It had to be 75 centimeters cube in all inside of that little cup. So, the final mass, and they usually ask it in grams based on the formula. And in this question, they did say to assume, well, usually they would say to assume that 1 centimeter cube is equal to 1 gram. Right, so you can look out for that. So that's why they get to this point and they're saying that the final mass of the solution is 75 grams. So we're good for there. This is assuming
75 grams from the volume.
Yes, yeah. So you basically they're saying that 1 centimeter cube is equal to 1 gram.
So how come we found the moles?
Right, we needed the moles because we're going to use that in this part here now.
Okay.
Right, so we needed the moles because now we need to plug these things into the formula. I'm going to just clear up the screen a little bit. We don't need this calcium anymore, right?
No.
I don't think so. Alright, get these off of here. I don't need this perfect rectangle anymore. This. No, this.
So I have a question, right? You know how to use the ratio to find the missing like amount of water? You
Right.
always to find that?
Yeah.
Okay. It's always the missing amount of water.
Yeah, well, when you're doing the titration type, when you're doing the moles, you always use that ratio. It's called stoichiometry in order to see how much of the reactants are reacting with each other to produce the amount of product, because it's like a general ratio you could use for that particular reaction. So if I change the quantities used, so like how we move from using like for example how they react the 0.05 moles at 0.05 moles, if they change it now and say, well, all right, using 10 moles instead now, then you'll know, well, 10 moles of the sodium hydroxide had to react with 10 moles of the hydrochloric acid to produce 10 moles of water. Because the formula, the balance formula, gives you that ratio. Where you're going to apply that, take for instance, are working in the energy sector or something, right? And we wanna create steam, right? So we're gonna react the same sodium hydroxide with HCl, right? This might be a crappy example, but let's just say when you do that, you're gonna get steam, right? And I need to generate, let's say, I don't know, let's just say hypothetically they measure any steam in centimeters cubed. I could use the equation to work out the amount of moles of sodium hydroxide I need to react with a particular number of moles of hydrochloric acid in order to produce X amount of moles of the water. And then convert the moles to that volume that I'm looking for. So if my end target is, let's say, 1,000,000 centimeters cubed, I convert 1,000,000 centimeters cubed to moles, and then I go back now to the formula, and I'd say, well, all right, if the 1,000,000 centimeters cubed is equivalent to 1,500 moles, then I need to use 1,500 moles of sodium hydroxide with 1,500 moles of hydrochloric acid, based on that stoichiometry with the formula. You understand?
Mm-hmm.
Naomi, all right?
Yeah.
Kind of, yeah. You see, it's just like it's a generalization. What's a better analogy to use, right? All right. I know it don't really work like this in the kitchen, but say your mom give you this recipe for baking a cake or something, and
Yeah.
the cake is like to do like a 10-inch cake that would feed 15 people. And the ratio calls for 2 cups of flour with 1 cup of sugar and a half of butter. And then instead of 10 people, I want to make it for 20 people. So I double up on the flour, double up on the sugar and everything else. Same kind of thing with this. All right. We have 10 more minutes before this close off. I could send another link if we're not done. I just had to keep my eye on the clock because I had to do I have a class for trading starting at 8.
Okay.
Yeah. Right. So, right, we're at this point here now. Heat evolve. So, we got the final solution, mean 75 grams. We know the temperature rise was 9.1 centimeters cubed, right?
Yeah.
Now we're going to work out the heat.
9.1 centimeters.
Huh?
Yeah, can they give you that in the question?
Yeah, they did.
No, he said centimeters.
I mean, sorry, degrees
Celsius.
Degrees
okay,
Celsius.
You have 10 minutes.
Yeah. Right. So this is it here. We have the 9.1 centimeters cubed. This is the formula that I want to use here, guys. So final mass of solution, which is the 75 grams, because we use centimeters cubed to be grams. The rise is 9.1, and then the specific heat capacity of water going to be using is the 4.18.
Okay.
Yeah. Right.
If they gave you that it started at the temperature and ended at a temperature, just subtract them to find the change.
Exactly. That's what we're gonna do. Right. So when I work this out now, I'm gonna get this value here. Right. I'm gonna get this value of 2852.85 joules. Now, this is why it is we worked out all of this before, because we need to know that this volume of 75 centimeters cubed and this temperature rise is not related to 1 mole of water. It's related to 0.05 moles of water, based on that equation that we had before, because we wasn't working with 1 mole of water from the beginning. Because from the beginning, we've been working with 0.05 moles of sodium hydroxide, 0.05 moles of hydrochloric acid, and based on the equation, this 0.05 could only liberate a 0.05 moles of water, right? But going back to our definition for the heat of neutralization, they're saying that the heat of neutralization is the energy occurs when 1 mole of water is formed during a neutralization reaction. So in all of these reactions that they give us, most of the time you're not going to be working with 1 mole of water. You're going to be getting a different amount of moles, and you're going to work out what the heat capacity is, but then you need to find out for 1 mole of water. So this figure that we got here was 0.05 moles of water. So to find for 1 mole, we have to divide by the 0.05. Yeah? When I divide by 0.05, ironically, I get this amount, 57,057 joules, or we could convert it to kilojoules, so it becomes 57.057 kilojoules. And we know that the reaction is exothermic because we had a rise in temperature, so it meant that heat was given off. So it's negative here. Notice they have the negative sign, right? Yeah. Negative 57.06 kilojoules per mole. And
why did they put the negative sign?
Why they put the negative sign?
Yeah.
Because it's an exothermic reaction, right? Since the reaction is exothermic, it means that the energy change has to be negative. And that goes back to remember the note yesterday where I was telling you exothermic reactions, they give off heat.
Yeah.
Right? And they give off heat because the reactants are they have more energy than the products. And remember that formula for enthalpy change.
Yeah.
That formula for enthalpy change is the H products minus the H reactants.
Reactants.
And in this case, the reactant's going to have more power, or it's going to have more energy, so the overall value that you'll get for the enthalpy change is going to be negative.
Negative. Oh,
yeah.
Okay, that makes sense.
Right? So that's what's happening there. So quickly before we get bumped out of the session, let me just clear everything. It's been recorded, so when the session is over, I would upload it to YouTube and then send you the link.
Okay.
Right? So you can view that. This one, I don't know if you're gonna get enough time, but it's the same thing. 2 molar solution of sodium hydroxide, hydrochloric acid, measure out 50 of this, 50 of that, pour sodium hydroxide, polystyrene cup, measure temperature, add acid to the sodium hydroxide, stir the mixture, record the highest temperature, right? Aim, basically you're gonna be finding the heat of neutralization of acid and alkali, or you could put specifically of sodium hydroxide and hydrochloric acid, right? Method of procedure, you could kind of take your time and work that out. You're going to need to measure out the 50 centimeters cube, right? Then you're going to have to measure the same thing out for the 50 cm cube, or 2 molar hydrochloric acid. What I'll do is I'll probably see if I could get, because for these labs, right, it's better when you see it.
Okay, a video.
Yeah. But this part you would understand because the data to be collected, so you know you're going to be checking temperatures, right? And then this other part, steps for doing calculations, you'd be able to do this as well because you know you're going to have to take the different temperatures you get in order to look at the temperature rise and work out. You're going to have to work out what the heat of neutralization is.
Okay.
Is this a paper 3 by chance?
No, this is a paper 2.
Okay.
This is a paper 2. Yeah. So what I want you all to do is to just try to mock up something like this, right? Pay attention to the marks they have on the side here. That would help you in terms of how much detail you need, right? So 1 mark, 2 mark. You know, they're not asking for too much there. 3 lines you have for the method of procedure, so they're not asking you to write a thesis.
Okay.
And we'll probably meet again before next class, and we could probably compare what we came up with.
I have a question. Isn't
Uh-huh.
the method of procedure what they wrote up?
Pretty much. But you're gonna have to kind of put it in your own words.
Okay, cool.
But look for a video online and send that to you so you can actually see what takes place, and then that will help inform how you're gonna write the method or procedure.
Okay, cool.
Okay.
Yeah. All right, guys. Thanks for your time.
Thank you, sir.
No problem. I'm gonna stop the share and I'm gonna forward it. I'd have to upload it to YouTube and then send it to you guys so you get before
Okay.
tonight.
Okay.
All right. Take care.
Thank you,
Bye,
sir.
everybody.
Bye.
All right.